Finding the volume of a solid of revolution, the disk method. Now, when I say disk, as in disk method, you need to be thinking like a hockey puck, shown here, or a drink coaster, or a cake, or a cookie, or a pie. Don't think of a compact disk, also known as a CD, because there's a hole in a compact disk. My first question to you is, let's say that I had this rectangle, and I wanted to take this rectangle and rotate it 360 degrees around the x-axis. What shape would that be? Before we get to the answer to that, this rectangle can be created by simply doing the equation y equals 5, which is just a horizontal line, and then finding the area underneath it from 1 to 3. What I have here is a software called Autograph, and I'm graphed the line y equals 5. It's right there in blue. And this is pretty cool because I'm looking at my axes in 3 dimensions. I just hid the z-axis there. Now what I'm going to do first is I'm going to find the area underneath that curve from 1 to 3. And there it is, showed up in this beautiful pink color. Okay, so we just have a rectangle. Now I'm going to take that rectangle and I'm going to create the volume of that rectangle, and I'm going to rotate it around y equals 0, which is the x-axis. And what do you think is going to happen? We have a cylinder. Now you might call this cylinder like a really fat disc. Okay? I have another one here. This is the line y equals x, and I found first the area underneath y equals x from 0 to 3. And again, I'm going to take this is a triangle, and I'm going to rotate it around the x-axis. I want you to predict what shape will be created after I rotate it. All right, let's have a go. Create volume, y equals 0. Here we go. We have a cone. If you said cone, you would have been correct. Now, obviously, with this one, that's just a cone, and the previous one that was just a cylinder, we can just use the formulas that we learned in geometry class in order to find those volumes. But what if it was much harder? For example, what if I had this situation? This blue curve is the function y equals x squared, and then I looked at the area underneath it from 0 to 3, and that's what we see there in pink, and I'm going to rotate that area around the x-axis, and I wonder what kind of shape we're going to get here. Create volume around that axis. It looks to me like a Hershey's Kiss. You could project or theorize what you think it looks like. So the question now is, how am I going to find the volume of this Hershey's Kiss looking shape? Sort of like a cone, but instead of it having just a straight edge there, it's curved like so. How are we going to find that volume? Well, let's go back a minute. And maybe here, instead of just using this general technique, I'm going to use rectangles like we did when we were doing Riemann sums. I'm going to do right rectangles, and I'm going to do 4 divisions. Now, we talked before when we were doing area that obviously if I added up the area of all these rectangles, that's going to be an overestimate of the area under the curve from 1 to 3. So if I take these 4 rectangles and I rotate them about the x-axis, I'm going to have an overestimate of the volume. But let's just have a look at it anyway. Create volume. And what we have here is a bunch of cylinders, or discs, you might call them, that are stacked on top of each other. Sort of like when you have toys for children. That's what it reminds me of, probably because I have a child. So hopefully you agree that we could find the volume of each of these 4 cylinders and add up those volumes, but that would give us an overestimate of the volume of that Hershey's Kiss shape that we saw before. Well, what if I were to have more rectangles? So let's go here, and maybe I'm going to have 8 rectangles from 0 to 3, and I'm going to find that volume. I think you can agree that that's going to be a better estimate of the volume of the Hershey's Kiss shape. If I had 16 and I rotate that around, 16 rectangles and I rotate that around. that is going to be an even better estimate of the volume of that Hershey's Kiss shaped thing. So much like we were doing before with the Riemann sums, we need to think about taking an infinite number of rectangles that are infinitely thin, and we're going to rotate them all around the x-axis, and we're going to create these infinitely tall cylinders. Okay, when I say tall cylinders, it's because the height of the cylinder, because these cylinders are sitting on their side. All right, the radius of the cylinder, oh look, it moves by itself. Stop. The radius of the cylinder, now it's going faster. The radius of the cylinder is that distance from the x-axis, that's our axis of rotation, up to the point on the curve there, okay? And then the height would be this horizontal distance here, or you might call this the change in x, which is the height of the cylinder. We'll get more into that in just a minute. All right, so for a definition of a solid of revolution, this is going to be generated by taking a plane region or a two-dimensional region and rotating it about a line that we would call the axis of revolution. So many familiar shapes are this type or created this way. So we saw before, if you take a rectangle and you rotate it around its axis of revolution, you get a cylinder. A semicircle will lead to a sphere. A triangle will lead to a cone. And if you have a rectangle that you rotate about, excuse me, another axis of revolution that doesn't touch the side of the rectangle, you're going to get a hollow cylinder, which we're going to talk about that in the lesson with washer method. So here's just another demonstration about the function y equals x squared. If you rotate it around, you get this Hershey's Kiss shaped solid. And in order to find that volume, we think about partitioning it or dividing it up into a series of discs, an infinite number of discs that are infinitely thin, sort of like a communion wafer, if you will. And in order to do that, we're going to end up, in order to add up an infinite number of cylinders, we are going to be, or infinite number of discs, we're going to do an integral. Yay! So let's go back to a geometry class and remind you about the volume of a cylinder formula. Remember, it's going to be the area of the base times the height of the cylinder. And since the base is a circle, then we're just going to do pi r squared times the height. But these discs or cylinders are sitting on their side. So the height of the cylinder or the disc is this direction horizontally, and then the radius, which we're calling big R, is the distance from the x-axis, or the axis of revolution rather, out to the edge of that rectangle there. All right, so there's little h and there's big R. Now we use big R here because when we do the washer method, we're going to have a big R and a little r. So again, the volume was area of the base times the height of the disk, so pi big R squared times h. And we're going to take that. We want to find the volume, though, of all of those disks, which we can do some math magic, which I'm not going to show you. But it's just going to end up being pi, and then you're going to do the integral of r squared dx. So let's take a look at this. The pi, of course, is a constant because I could put the integral sign here. But pi is a constant, so I take it outside of the integral. And then r squared, that's just going to be whatever the radius is. And then the h, that's the dx. So your h, or the height of the cylinder, is your change in x because it's going horizontally like that. So the h becomes the dx. Now the radius, of course, that's going to be whatever your value is of your function at that point. So the radius is going to be the value of the function f of x. In other words, and you can pause the video and read all these things if you want, we have this. The volume of a solid of revolution, if we're doing the disk method, is going to be pi times the integral from a to b of big R of x, quantity squared, dx. Write that down. This is going to give you the sum of an infinite number of disks that are infinitely thin, like a communion wafer. So just more images here to show you how it works. So let's take a look at our first example. So this is the function that we were just working with in the autograph software. So y equals x squared from 0 to 3. And so that formula is going to be pi times the integral from the lower bound will be 0 and the upper bound is 3. And then you're going to do the radius, which is just your function. So x squared squared dx. And remember, that's just because the radius here from the axis of rotation up to that point there, that's just going to be whatever your function is. That's going to be your radius. And then, of course, the square comes from the formula for volume of a cylinder. Now I'm going to work this out by hand. So it's going to be pi times the integral from 0 to 3 of x to the 4th dx. So the antiderivative of x to the 4th, that's going to be x to the 5th over 5. We still have this pi out here, and we're evaluating it from 0 to 3. So that's going to be pi times 3 to the 5th over 5 minus 0 to the 5th over 5. Of course, that's just 0. So it's going to be pi times 3 to the 5th is 243 over 5. And so we have 243 pi over 5. And if you were to do this in your calculator using Math9, which you're totally allowed to, you can do just this portion of it in the calculator, and that's going to give you the 243 over 5, and then just slap the pi right next to it. Let's take a look at our next example. Try this one on your own. So here we're looking at the function y equals the square root of x, and we're going from 0 to 1. And the diagram is given to you, which is quite nice. So this is your function y equals the square root of x. So the volume is going to be pi times the integral from 0 to 1, our lower bound is 0, upper bound is 1, times your function, which is the square root of x, squared dx. And again, I'm going to work this out by hand, but you're welcome to use your calculator. Pi times the integral from 0 to 1 of just x dx, which is going to be pi times x squared over 2 that we're evaluating from 0 to 1. I'm going to put a little square bracket right there. So now I'm going to have pi times 1 squared over 2 minus 0 squared over 2, which is going to be 1/2 times pi, or in other words, pi over 2. Of course, if you want to do this in your calculator, and you just do the integral from 0 to 1, your calculator is just going to give you 1/2 and then multiply by pi, so pi over 2. Try this one on your own. Now, if I were to do a sketch of the graph here, because the graph was not included, y equals e to the x. If you don't remember what it looks like, of course, you can graph it in your calculator, but that's just going to be a simple exponential function. And we are going from -1 to 2, so somewhere over here, -1 to 2, and we are going to take this region here, and you're going to rotate it around the x-axis. So it's always good to indicate which is your axis of revolution, or your axis of rotation. So we're going to have then the volume will be pi times the integral from -1 to 2 of e to the x squared dx. Now I'm going to work this out by hand, but I definitely would encourage you just to use your calculator for this one. That's going to be pi times the integral from -1 to 2 of e to the 2x dx. That antiderivative, you can use the u substitution if you want. I'm going to use the linear shortcut, and it just ends up being 1/2 times e to the 2x. So we're going from -1 to 2. So that's going to be pi times 1/2 e to the 4 minus 1/2 e to the -2. So that's going to be pi times e to the 4th over 2 minus 1 over 2e squared. Not a very pretty answer at all, but if you do the approximation for that, you're going to get 85.55 is the approximate volume of the solid created when you revolve that around the x-axis.